Hey guys, it's Tom Cherry Holmes with the FujiNet project, giving a little status update on the N device. Now, I've been spending a considerable amount of time essentially building the plumbing required to abstract multiple protocols that can be used through a single device. This has taken a lot of very careful thought and a few rewrites to come up with something that works with the stated goal of essentially only using a handful of abstract commands: open, close, read, write, status, and special, to handle the myriad of different protocols. And to get the SIO level of this working correctly by writing a series of test programs which exploit each of these commands, and to use these to debug that functionality until it is stable enough that I can move on to the CIO functions. We can see right here my development environment right here, and what we see here is actually a debugging window that actually shows status information that's coming in from FujiNet here. If we actually pull this out a little bit and take a look, we delve in. Last time I actually went through the various workings of the network device, basically breaking out into each of the individual abstract commands, of which I've added a couple of special things onto the end of this, pardon the pun. What is special? Special is any command that does not immediately fall within the standard idioms of open, close, read, write, status. And those are typically declarative functions which set various communication parameters that need to happen. Such as for TCP, we need a command to accept an incoming connection if we're listening for a TCP connection. Or we need a special command to set the destination address for a UDP packet if it is not indeed the packet that we have either received from or have already connected to. Things like that, and there are others, but I needed to come up with a way to basically tie all of this together to something that really made sense. And for this, I essentially made a series of functions which return whether or not, for a given protocol, if a command is actually supported. And they're delineated by, you can see right here, 00, 40, and 80, which correspond to the SIO dstat-s flag, which specifies whether the SIO command in question sends data to the computer, whether the computer sends data to the peripheral, or whether no data interchange and therefore no payload is actually sent, and we're only supposed to send whether or not the command completed properly. You might think, well, wouldn't all commands actually handle payloads? No, actually, some of them don't. In fact, there may actually, in some cases, be enough information in the command frame to an SIO for an SIO command frame to be able to complete a particular action, such as accepting a TCP connection. We do not need any additional information for that because the ESP is already holding the particular file descriptor of a pending connection in its buffer, and all we have to do is acknowledge it and tell the ESP to take that file descriptor and hold on to it so it can send data to it. So there's no payload needed there. Another command that you don't need any sort of payload for is the close command, for example, and so on. So we had to take and create a series of commands which basically determine whether or not, given a protocol, if a particular command is actually supported or not. You can see the special supported 00 here, and here is our 00 command for accept. If it's accepted, so we return true. Otherwise, nothing else, we return false. Nothing else is currently supported. And we've broken out the commands for the special into their appropriate logic. You can see inside of each of the protocols here there are no SIO commands to send data to and from the computer. The whole purpose is to abstract all of the protocol-specific actions into their own class, have them do whatever data manipulation is needed, and to pass that information back to the SIO network device here, which actually does the requisite SIO protocol negotiations. So with that, what do we have here? Well, you've seen the TCP device. You see that we have, basically buffer sizes here being passed through, and the status buffers and everything else. The TCP, since TCP has the concept of a connection between two hosts, we need to know whether or not this has taken place or not. Whereas with UDP, we do not need such information. And so you can see the implementations. If you pull this up and take a look, you can see that the implementations for UDP are considerably simpler because we're only dealing with the formation, the sending, and the reception of individual datagram packets. Now, as an aside here, if you have not written any TCP IP applications before, you might be asking, why would you want to worry about whether or not you're using TCP or UDP? TCP can best be described, at least in my humble opinion, as taking a cable between one host and another. If you're familiar with RS-232 serial cable, it's essentially the same thing. And what TCP actually does is TCP builds on top of IP. It's actually, you can think of it kind of as if you were to take all of the bits and pieces that you would use in UDP for sending individual packets, add the ability to have sequence numbers for each of these packets so that they can be checked and reassembled in the correct order on the other end of the line, and have bits and pieces to maintain and negotiate a connection state between two endpoints, then you have most of actually what TCP actually is. And I find it rather funny actually that people that use UDP often wind up reinventing huge portions of TCP in the end. For one reason or another. There are valid reasons to do so. But the thing about UDP, on the other hand, is that UDP, or User Datagram Protocol, is only concerns itself with the transmission of individual packets, which it calls datagrams. These datagrams are of a fixed size, typically anywhere from, say, 0 bytes to typically no more than 576 bytes at most. The reason being is that routers tend to want to only pass packets that are smaller than what they call the maximum transfer unit. And for most internet connections, the MTU is typically something like 576. This means if you try to send anything bigger, then the router will break up the packet or fragment the packet into smaller packets to send over to the other host. Now, if this happens, it becomes your responsibility to determine whether or not this has taken place and to reassemble the packets. And this is a big reason why protocols like TCP have sequence numbers, to aid basically in this packet reconstruction exercise. Now, I say all of this because some people actually do definitely need a background. They haven't written TCP/IP network applications, and they need to kind of be aware of some of the differences back behind. Because you can choose some choices are better. Some of these choices, either TCP is better for certain things, UDP is better for others. For typical serial port-like applications where you have two endpoints that are sending streams of data back and forth, and you don't want to have to worry about breaking that data up into individual pieces, and you just want to deal with it as a stream, TCP is a very good choice. And in fact, protocols like HTTP are built on top of TCP. However, there may be situations where you want to deal with fixed packets of information, and you want to be able to take those fixed packets of information and put them together effectively. The reason being is that TCP kind of falls flat when you need to send to multiple people, because TCP pretty much dictates that you need to create, for each individual participant that you want to send the same piece of information to, you need to create an endpoint, a connection for each of these individuals. Now, because FujiNet is built on an ESP32, and an ESP32 is indeed an embedded microcontroller, while the TCP/IP stack inside of the ESP32 is full-featured, it does have some arbitrary limitations, and one of those is the limit to the number of simultaneous TCP connections that you can have at one time. By default, this is 4. It can be raised to 8 by modifying some parameters in the underlying toolkit, IDF. But still, you have a limited number of connections that you can make. To get around this, I'll say that another way. In contrast, UDP, since you are sending individual packets and you're just saying, okay, this packet needs to go to this destination, this packet needs to go to another destination, it doesn't matter. There is no connection between point A and point B. You're just sending the packet on its way, and the routers will take care of routing that packet to its destination. So that means that if you wanted to create a large multiplayer game, say 8, 16, 32 players, 64 players, whatever, and you want to use a FujiNet for this, you are going to have to use UDP. And for certain things where packet sizes are fixed, indeed, having the fixed packet size of UDP is extremely desirable. I will say, as a final caveat, that UDP does have its disadvantages, the biggest of which is that because there is no sequencing, packets can arrive on the other end out of order. They also cannot arrive at all. It's a possibility that the packet may not arrive at all and may need to be resent. These are things that you, as the application developer, need to be aware of and accommodate in the designs of your programs. So with that, we'll actually go forward now with what I've been doing here. So I've implemented both TCP and UDP protocols in the stack here. And we'll actually take a look and see them in action now. We go ahead and go to my terminal, and we can actually see, if we open up my upload and monitor here, we'll see that FujiNet's active. We'll go ahead and reset the FujiNet for us. You can see that the debug message comes up, the config gets loaded. And you can see that we're connecting to the network. Now I have set up in my drive slots two things in my drive slots. The first is a copy of OSA Plus 2.1. The second is the test program sitting in drive 2. I'm using OSA Plus 2.1 because it's small and it gets out of the way and it allows me to quickly go ahead and iterate through these test programs to take and debug these various problems. Go ahead and boot it. And as you can see, with the combination of the high-speed SIO and the fact that OSA Plus isn't all that big, it boots up very quickly and shows me my network configuration and promptly gets out of the way. You saw before that if I did a network open, and I start up a netcat here, we connect, and you'll see that the connection is received. You'll also see that the individual portions of breaking apart the device spec into its path, port, and its protocol components, and then passing those pieces of information over to network protocol TCP, where it opens up the connection, sets everything up, and finally says everything's okay, so network CPP sends a complete. And from my end here, you can see, yes, the connection is indeed opened. And if we go ahead and write a message, we can see that the write actually happens. Conversely, if we take and send something back, make sure I'm on the right window. We can get a status, which gives us hex 18 characters available. And if I actually take and just for a moment here, open my calculator here and just can quickly convert that should be what, 30? Yeah, that should be 30, but I'll double check anyway. 24. Yeah, octal 30. Wow, I'm thinking an octal. Okay, so we have 24 characters waiting for us, and we can go ahead and grab them. And we can see that there it is, ready to go, sending something back. Bam. We can see that the data comes back nice and nifty, right there. So we can see TCP communication is working at the SIO level. It's working, doing great. We can close the connection, and we can see that the connection has been dropped, and the destructor has been called here, which cleans up the TCP protocol, frees all of its buffers, puts everything back up on the shelf, so to speak. Conversely, we can now open a UDP port. Now, UDP is kind of special because essentially, as before with TCP, you can put a host name in here. Or you can choose not to. The difference here is that when you open with a host name in the path, it does not open a connection to that host, but rather simply makes note that the next time you do a write, that that host and that port is where you're going to send the destination packet to. Conversely, it also opens a listening port of the same port number on the ESP32 so that packets can be received back. So if we go ahead we can see that our UDP is now opened, and you can see now as part of the, we can see that we're using the UDP protocol here, the constructors and the open methods from the UDP open here to do all of the low-level bits and pieces that we need. Yet from the Atari side, if we conversely go ahead let me see here. Excuse me for just a moment. I actually need to it's off the screen, that's why. We can go ahead, and actually I'm going to see if we can see this because my window is obscuring this. We can run the UDP receive program, which if we take a look at it real quick, we can. Let's just take a look at it. It's a very simple little program that simply opens up a UDP socket on 0.0.0.0, which means listen everywhere, listen on port 2000, and if we receive a datagram, grab it and print it with a maximum size of 1024 bytes here. Great. So if we go ahead and run it, and we send some data, we can see here that we're sending a full-sized packet, which is essentially by default the send and receive buffer here is 256 bytes, so we're literally seeing 256 bytes of data sent at a time. One of the special commands literally is going to set the send and receive buffer here so that you can match the UDP packet size. Write some more data. And you can see very much so that we're using the same exact programs that we were using for TCP to send UDP data as well. And the FujiNet is gladly taking and abstracting all the bits and pieces away from the Atari. So the Atari only has to deal, at the SIO level, it only has to deal with a properly formed SIO block, device control block, with the relevant information, the relevant buffers, etc., how big it is, and then it's off to the races. Conversely, if we go ahead and use UDP, we take a look at UDP-PY real quick. We can see that this is a program that basically sends a test message. Very, very simple. It just takes and sends a test message back to the Atari here over UDP. Now, if we do a status at this particular point in time, we'll actually see all zeros. I recall before, the convention is the first 2 bytes are the number of bytes waiting in the buffer. Since there's not a packet waiting for us, those are zeros. There is no concept of a connection, so the connected byte is also 0, and the 4th byte is reserved, is not being used yet. So everything is all clear. Believe it or not, this is okay. Again, UDP is connectionless, so this makes perfect sense. If I go ahead and send using the UDP test program, we send the test message, and we do a status, and we can see roughly hex 10 or 16 bytes waiting in the buffer for us. Now it's important that when we see that there is a packet waiting for us in the status buffer, that we need to immediately read it, because the very next time we do a status, that packet is gone. That packet only exists for one call of the status register here. That packet, it serves to underscore the ethereal nature of how UDP works. I'll have to send the packet again in order for it to be received. And it looks like my alright, looks like I may have a bug. We'll try that again. I may very well have a bug here. Let's see what happens if I take and do a read. Let's see if it does it. Yes, okay. So it looks like I have a slight bug waiting here in parse packet. There's nothing to read here. If I do another read here, there's no more. There's a packet, and the packets that we're waiting. Is there anything else? There may, okay, this may very well be a bug. Okay, so now we've buffered the packets here. There's nothing else to read. Wait a minute, nope, okay. So I guess there is, looks like I need to take and do a little buffer clearing here. But you can see there's more that needs to happen. If I take and, let's go ahead and pull this away now. Let's see if something else can make it in here. Now the 9B, as I recall, is an EOL, a TASCII EOL. I'm just going ahead and sending that across as a convenience. Doesn't have to. But if we go ahead, test message being sent, we can see it right there. And that's, nah. Let's see if, nah. Okay, looks like some slight bugs needing to be fixed here, but as we can see, we're using the same bits and pieces in order for reading and writing in order to abstract everything nice and neat on the Atari. And like I said, this is in development, so I am squashing bugs. We'll go ahead and just close that connection. It doesn't really, there's no connection to close, but it does tear down the UDP connection so that there's nothing listening there. But if I go ahead and open it again, and you can see here a slight little wait there. Okay, now it's opened again. We go ahead and send a test message here. We go ahead and there we go. And there we go. So again, it's just more bits and pieces of things that we know we need to take and work out here. But I hope you guys are starting to see the point. I'm going to go ahead and end the video here, but I wanted to kind of show you guys where things stood at this particular point in time. And I'll be spending the next couple of days, basically bits and pieces of off time here, cleaning this up, trying to get this particular layer shored up so that within the next week or two, I can start working on the CIO driver. So until then, as always, have fun.